Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC2006. Today we are going to continue with our lecture, which is lecture 3. So I always like to recap on what we have done previously. And in the last lecture, I introduced to you this table of different isotopes and spin number, and this is the natural abundance. And as you can see here from the table, proton has the highest value of gyromagnetic ratio, and the natural abundance is 100, and you have the spin being half. And we are going to focus mainly on the proton NMR. And towards the end, I'm going to just talk a little bit on carbon-13, which is usually the complementary to the proton NMR. So if the isotope has no spin number, so it's going to be NMR inactive. So examples of that are the carbon-12 and oxygen-16. So this is just an example of a table, so I may have various versions of tables, but the numbers are going to be the same, but a different representation of that. So this is just an example so that you can see that. Not entirely sure the nature of the negative and positive values here, but usually when we report the frequency, I'll give it in the positive values. Okay. On top of that, you were also given this figure, and I hope you remember why, in spite of the proton and nitrogen 15 having the same value for the spin number, but you can see here apparently that the Zeeman splitting for the proton is much larger than that of the nitrogen 15. So if you do not remember why that is so, so I highly suggest that you look back at the lecture video from last week. Okay. Now I gave you this, I showed you this picture even in lecture 1 and lecture 2, and today we're going to expand on this. Right, so we're going to start with the spin properties of nucleus of an atom. So certain atomic nuclei will have spin, as we have seen before, and when it has spin, it will have spin angular momentum, which is labeled by P. And because it is a vector, so you can quantify it via this equation. So P is equals to square root of this spin number, spin quantum number plus 1, and times the h bar, which is just h over 2 pi. And we have also talked about that depending on the type of nucleus, I can either be integral or have integral, okay? And that depends on the mass number and so on, okay? So, but for this class, the values are just going to be given. And if I is equals to 0, there will be no spin angular momentum, and so it's going to be NMR inactive. So as you know, that spectroscopy is technique is very much related. The mathematics is related to quantum mechanics. We're not going to spend on that, but enough for you to know that because of that, it's quantized, the orientation of the spin quantum number, and the angular angular momentum. So the vector can only point in certain directions, and specifically because this is NMR actually aligns along the z-axis. So we're going to look at PZ, which is equivalent to the quantum number times that times h bar. Okay, and the quantum number can take the values of I till negative I, and that will make up to a total of 2I plus 1 values. So a nucleus with spin angular momentum, as we have discussed previously, it behaves like a magnet, tiny magnets. And because of that, you have this you have another physical entity associated with that behavior, which is the magnetic moment mu, which is proportional to this angular momentum by this mu is equals to gamma times p. And gamma, as you know, is the gyromagnetic ratio, so every nucleus will have their own unique gyromagnetic ratio. In some textbooks, they will call it magneto-gyro ratio. It's actually the same thing. And since we're focused on the direction of the z-axis, so the subscript is going to be written in z. Okay, and the value of gamma can be either positive or negative, and that depends on whether P and mu are either parallel or antiparallel to each other. So that depends on, that will actually determine the signage of the gamma. So when you apply magnetic field, as in you put your nucleus in this NMR spectrometer, so you have this very strong magnetic field. So the energy of the interaction between the nucleus with a magnetic moment and the applied magnetic field is given by this E is equals to minus mu times B naught. And of course, you have this Cartesian axis with the different directions, but because we are only focused on the z direction, and so the values will only pertain to the one in the z direction. And so you have a string of equations just now where you have this magnetic moment and this spin angular momentum. So if you plug that into this equation, you will eventually get that the energy is equals to minus gamma, and you have this quantum number times h bar and b naught. Okay, right. So because our focus is on the spin half, for example, the proton or carbon-13, so based on that, since m can take the value from I to negative I to I, so that means that the values that you will get for m here is plus half and minus half. Now I will usually have reminder box here to remind you of the equations that we been using in the previous pages, so you don't have to flip, and I also don't have to flip. So I hope this is helpful. Okay, and so if you take that, so that means you have one value is when it's plus half, that pertains to that refers to the alpha spin state, which is the low spin state and sometimes called spin up, and and the opposite is negative half, which is the high spin state or the beta spin state, and sometimes we call it spin down. So in the absence of magnetic field, alpha and beta are actually equivalent. They have the same values of energy, so as you see here, so we call it degenerate. But as soon as you apply the magnetic field, this degeneracy is broken, so you have this splitting, and this splitting is known as the Zeeman splitting. So you have here the alpha being in the lower state and beta being in the high state. So the positive half is here and negative half is here. Okay, so if you plug that into that the energy equation, so this energy is then equivalent to minus half gamma h bar b naught, as you can see here from equation 9. And for the energy value for the beta spin state is going to be this, that. But our concern is what is the energy splitting, the difference in energy. And all you have to do is just take the value of the energy at the beta spin state minus that in the alpha spin state. And that gives you the equation gamma h bar b naught. So there you go. So I hope that, as much as I can, when there is an equation, I like to share the derivation, how the equation is derived, so that you're not just accepting the equation, so you understand where it comes from. So so this is something that you need to remember. This equation is very important, but in cases where you can't remember the equation, so if you remember how it is derived, so you can actually derive it yourself, and then eventually you come up with this equation, and it's much more exciting and satisfying to actually derive an equation as well. Okay, so now when a sample is irradiated with this EM radiation that has this frequency of mu L, and that means the photon energy of this. So then you have this transition occurring from the alpha to the beta state. Okay, and that means that you have this equation. So the resonance that we talk about, you can actually explain it mathematically as well. So you have here the energy splitting, which is if it equals to the amount of radiation that's being supplied. So then you actually fulfill the resonance condition. Okay, and if you rearrange the equation, you will get this equation 13. So, and this is known as the resonance frequency, or better known as Larmor frequency. So, and that's given by gamma being naught over 2 pi. Again, this is another equation which is very important that I want you to remember. But in case, again, if you can't remember where this comes from, you just have to remember the resonance condition here, and you can derive it. So the Larmor frequencies of nuclei will in NMR, because it's NMR, so it will lie in the RF region, radio frequency region of the EM spectrum. And the value gamma will depend on the type of nucleus. So each nucleus will have its unique value of gamma. And the magnetic field is certainly fixed, the applied magnetic field. So hence this Larmor frequency will also depend on the type of nucleus. So if you look at, for example, the Larmor frequency for several nuclei, let's say at a magnetic strength of 2.35, you will see that the, for example, you have here a few nuclei. So you have the proton at 100, carbon 13 at 25, you have fluorine at 94, and phosphorus at 40. So then, so I'm going to hold on to this first. So you see that this Larmor frequency will depend on the type of nucleus. Now remember that I told you that sometimes there are subtleties in NMR in my lecture, and sometimes even in the picture. So this is one example. Now you see that these machines the spectrometers, is you can see the labeling, the number labeling have 400, 300, and 700. So what does that mean? What do these numbers actually tell? Well, these numbers actually base or label the spectrometers are actually labeled based on the proton proton nucleus on the hydrogen. So you can see, so this is actually the Larmor frequency for the hydrogen or proton. So that's what it means. So if we look back at this previous, okay, based on this, and you can actually calculate this by using the equation for the Larmor frequency. So you see here the Larmor frequency for the proton is actually 100.04. That's close to 100. So you can expect that the label on this spectrometer is going to be 100 megahertz. So there'll be a 100 label on the machine to specify that, you know, it's the Larmor frequency of hydrogen. Okay, so that's what it means. So those numbers mean something. It means that those are actually the Larmor frequency for hydrogen. Okay, so that's the subtleties, that one of the subtleties that you will see. Okay, now in terms of sensitivity, it's proportional to gamma cube, and in comparing that, obviously that this you can expect that the sensitivity of proton NMR is going to be very large as compared to that of carbon-13, for example. And so this is what this slide talks about. Okay, and I like this, you know, if you were to actually define the NMR experiments, and I put here in essence, you know, what it actually means is that it studies the properties of molecules containing magnetic nuclei by placing the sample in a magnetic field, and irradiates the sample with an electromagnetic radiation in the RF region. And it doesn't stop there, which fulfilled the resonance condition. So that's complete. You know, it in a magnetic field, RF region, and then has to fulfill the resonance condition. And I also need to highlight that, now that I remember that, just because that this is labeled 400, 300, 700 based on the proton NMR, proton nucleus, it doesn't mean that you can only run proton NMR. It means that you can run any other nuclei, and so this is just a labeling. Okay, so as soon as you use another, you're running another nucleus of NMR, so the Larmor frequency will definitely change. Okay, and the other thing about running the experiment, doing it experimentally, you want to make sure that you have a stable and homogeneous magnetic field. Otherwise, it's going to disturb the signal of your spectrum. Okay, and liquid helium and liquid nitrogen will also, you have this superconducting magnet, and you have this helium, liquid helium and liquid nitrogen, which protects it. And as samples are sometimes rotated so that you will feel the same magnetic field, so you can have this homogeneous magnetic field. So the modern NMR will actually involve the pulse NMR. What that means is that a short radio frequency pulse, which is applied to saturate both energy levels in the sample, and the nuclei will return from the upper energy level to the lower energy level, emitting the radio frequency energy, and then that will be recorded as a decay curve. And this decay curve So this is actually the actual signal of the NMR, which is called the free induction decay, also shortened it's also called FID, free induction decay. And this is the labeling here, in the x-axis is actually time, so in seconds, for example. So this is time-dependent spectrum. Now, for a spectroscopist, this is something, they can actually decipher some, a lot of information from this. But for normal users, which are most chemists, okay, and so this may not be visually understandable. So you need a mathematical tool, equation to actually transform that to something which is visually easier to decipher. And this mathematical tool or equation is called the Fourier transform. And so with that, you will have this frequency dependent spectrum, and this is something that that's something that you're familiar with. Okay, and this is frequency dependent, so that means the axis here will either be hertz or ppm. Okay, so let's talk about population of energy levels. So suppose that you have this proton and the applied magnetic field is 1.41 Tesla, and if you calculate the Larmor frequency, that's about 60 megahertz. The energy difference given is 2.39 times 10 to the power minus 5 kilojoules per mole. So the thermal energy resulting from room temperature is sufficient to calculate both energy levels, because the energy separation is really very small. But in essence, there will always be a slight excess of nuclei in the lower energy spin. It's always the preferred state, the lower energy. And this magnitude of difference can be calculated by the Boltzmann distribution equation. So here you have that the ratio of the population in the upper state over that in the lower state is given by the exponential of the negative of the energy splitting over kT, and K is the Boltzmann constant, and T is the temperature in Kelvin. So, and delta N is the population difference of the two states. So this is another reminder box to give you some of the equations that you can actually use. So for example, at this temperature and at this operating spectrometer, there may be 9 nuclei in the lower spin state than that of the upper state. So that means you have these 9 more nuclei, 9 excess population, and that the excess population is very important in NMR. Okay, so when the 60 megahertz radiation is applied, it not only induces the transition upward, eventually it has to decay. So then if the population, the upper lower, become exactly equal, then you have this situation which is called saturation. Okay, and this very small excess in the lower spin state is important to NMR spectroscopy because it actually determines the sensitivity of the instrument. So so that's why you see here, if you increase the strength of magnetic field, spectrometer here, you will see that the values of the excess nuclei actually increase. And so when this increases, the values increases, the sensitivity of the instrument also increase because the resonance signals will be stronger since you have more nuclei that can undergo transition at higher frequency. Okay, and so that's why scientists would invest in a really powerful spectrometer like the 1 gigahertz that you see in Japan, because then you will increase the sensitivity. So what the sensitivity means, that means that you have better, higher, what do you call, resolution of the spectrum, and especially if you have complicated and really large molecules like proteins, so that you need really strong and powerful magnetic field. Okay, so pretty much that's what I want to cover today. So we talk about the energy splitting, the energy that corresponds to energy splitting, and we derive that. I didn't just give you the equation, so now you know where the equation actually comes from. And so we talk about the population, and we talk about the sensitivity of this spectrometer, which the excess nuclei will actually increase will determine the sensitivity of the magnetic field and hence the resolution of the spectrum. Okay, so these are questions that I'm giving you to actually I want you to do these questions. So I like to give questions at the end of my lecture so that you understand the materials. So the first one is, what is the resonance frequency of this fluorine nucleus in the magnetic field of 14.1 Tesla? And true or false, the Zeeman splitting for proton in a 400 megahertz spectrometer is smaller than that of phosphorus 21, and state your reason. When you have a sample has approximately 2 million proton spins, what is the population difference, delta n, of the nuclei in the upper spin state to that of the lower spin state, given that you have this magnetic field and the temperature as such? Okay, so you have all this time to actually attend, and I hope that you do, and we will talk about it, discuss on this in WhatsApp. All right, meanwhile, so take care and stay safe wherever you are. So thank you, and assalamualaikum warahmatullahi wabarakatuh. Bye for now.